Let ABC be a triangle with incenter I. A point P in the interior of the triangle satisfies angle PBA plus angle PCA equals angle PBC plus angle PCB. Show that AP is greater than or equal to AI, and that equality holds if and only if P equals I.
The difficulty is there are two kind of like major approach. One is by so-called finding a very nice bijection. A very nice bijection because they are counting out how many good sides you can have, and basically they are making some connections between good sides and arcs, and good triangles, those kind of bijection approach. If you go there, usually you are in a safer land because if you can set up that bijection clearly, usually you are okay. But more students do this problem by a more popular approach is doing by induction. And then they have some trouble about which part of the graph you are going to cut out.
I love geometry. I was looking for some hard geometry problems. I was sort of sad to see this as the first problem, just because I assumed it would be a bit easier. And it turns out it was. The problem is not very difficult. It took about, I think, 10 or 15 minutes to solve and write it, so I had plenty of time for the rest of the test on the first day.
Problem 1 really wasn't a problem at all. I think most of us looked at it, and in about 2 minutes, we had probably solved it and written it up. Yeah, it was, I think basically the problem was asking, if you've got a point and a circle, what's the closest point on the circle to the first point?
Turns out the angle condition on P places P on the circumcircle that goes through B, I, and C. Furthermore, that circle has center on the circumcircle of ABC. Call that center M. It turns out to be the midpoint of arc BC on the circumcircle of ABC. And once you know that P is on that circle, you know that A, I, and M are collinear, and so I, which is also in that circle, it has to be the closest point to A. And so certainly AI is less than or equal to AP for any other point P on the circle. And it turns out that's the entire proof. Let P be a regular 2006 gon. A diagonal of P is called good if its endpoints divide the boundary of P into two parts, each composed of an odd number of sides of P. The sides of P are also called good. Suppose P has been dissected into triangles by 2003 diagonals, no two of which have a common point in the interior of P. Find the maximum number of isosceles triangles having two good sides that could appear in such a configuration.
That problem took me a while, but I first considered small cases, like where I replaced 2006 gons with squares and hexagons and other even-sided polygons. And so I figured out that the answer should be like 1003 by checking the small cases. After that, I just basically knew it had to be some kind of induction, and I just tried a bunch of things, and eventually something worked.
Instead of looking at all 2006 edges at once, I looked at 3 of them, 4 of them, 5 of them, and inducted upwards. If you have a small portion of the polygon, at most half, that the total number of good isosceles edges is at most n over 2, if you have n sides of the polygon. And then I found a hole. And I just kept fixing and patching and fixing holes. By the time I finished writing it, time was almost up.
And I think this problem becomes kind of like a test stone for IMO student getting a silver medal or a gold medal, because many students were not able to write a very clean proof for this problem.
I just sat down, looked at it for a long time, and eventually we probably came up with something pretty similar to the official solution, which is talking about good isosceles triangles and great triangles and all sorts of things, but I think in the end my solution was probably a bit nicer, but it took me a bit more time.
Determine the least real number m such that the inequality absolute value of ab times a squared minus b squared plus the cyclic sum is less than or equal to m times a squared plus b squared plus c squared quantity squared. It's a gross inequality. So like I said, I only had about 30 or 45 minutes to work on it, which means I didn't get very far. The first step is to factor that big ugly expression in inside the absolute value signs. It factors as a minus b times a minus c times b minus c times a plus b plus c, which is nice to work with. I did find that, and I think that got a point or two. But then after that, you need a certain observation. You need the observation that we're probably going to have equality when a, b, and c are in arithmetic progression. And then from there are a number of ways to go. You can just sort of keep using inequalities that use the arithmetic progression condition, namely that c minus b equals b minus a. Or even more simply, you can make a substitution. You can say a is b minus x, and you can say c is b plus y, and then try to whittle it down to the fact that x equals y. So I didn't see that, and so I didn't make much more progress beyond the factorization, but it turns out that was the key. Well, either that or Lagrange multipliers, like Arnav tried.
As it happens, the approach which got the most points on this problem was Lagrange multipliers, which is maybe the most powerful technique of an inequality that you can think about, because it's basically just, here's an inequality, let's just break it down with calculus. And yeah, that's what I tried, and I would have gotten it completely if I hadn't made a mistake, which was very unfortunate, because when you make mistakes and you're using calculus, the graders are just like, no. So I think I got 2 points out of 7.
It's not a symmetric inequality. It's a cyclic inequality. And what happens if you change if you swap two of the numbers, it'll negate itself. So to make it symmetric, you would have to square both sides of the inequality, and that's just ugly because it's just too big. On top of that, you have to find the minimum value of this inequality, so you don't even know, you can't even like guess when the two sides, like what's the worst possible case. You don't even know that.
In a certain way, this problem is very good because students do lots of three-variable inequalities, and very likely they reach the best inequality case by either three numbers are equal, or two of them are equal, another one is on the other end, either one of them are evenly distributed, or two goes to extreme, one goes to another extreme, But this problem, the problem poser made enough algebraic manipulations to set this problem up, so the equality case is not that easy to see. So in that way, it's a very nice problem.